stopped my video, so I'm starting a new video. I'll post 2 videos of today's lecture. One for the first part and one in the second part. Yeah, that was part 1. Okay. All right, so guys, we have, thank you so much for the photos and the memories and all the stuff. I always like to tell people, if you guys don't sign up for my classes, I don't get to do this twice a week, and I really do enjoy it very much. So it's been really great. We've learned a lot of good stuff. It's been a very, very busy semester, that is for sure. So anyhow, I do have one more thing to share with you before we kind of wrap it all up, and then we'll take a break. We just proved the theorem that says that if we take the integral of the derivative of phi, we kind of get back to phi again. It actually works the other way around also. You can take the derivative of the integral of a function and you get back to that same function again. So I would like to also show that to you. It's kind of just the inverted version of this, and it's what we would call part 2 of the fundamental theorem of calculus. The one that's in your proof list for the exam is this one. It's the one we've already gone over. I should just ask, are there any questions here? Yeah.
The book proof uses the p-norm and theorem 6.3, which also has a p-norm. Are we allowed to use that one on the test?
The thing about the mesh, you mean? Like the sure. Yeah. So what Nkosi is talking about is, so maybe I guess I maybe neglected to write this down ever, but if you're you might want to write this down. It's not the worst thing in the world to have. We've used this a little bit, but I've kind of avoided the notation. Given a partition P, which is, in the list of partitions, we can define the norm of P as the following thing. And so it's put in these, this is what you're talking about, right?
Yeah.
The sort of these double absolute value bars. The norm of the partition, it's simply the max of all of the delta xi's. So this, if you just take your subintervals and you figure out the width of each of those, and you calculate the max of them, it's denoted this way. So yes, there was a result, I think last week, where I just wrote max of delta xi into my proof. If you would rather just use this notation, that's totally fine as well. Okay, so like for a quick example, if I wanted to know what's the norm of that regular partition of P sub n, remember that in that partition, you take the full interval from A to B and you divide it into n equal pieces. So this would just be the norm of this partition. So this is for each natural number n. Yeah, so you certainly can use that in a notation. It's probably not a bad idea. I should have written that down previously, but not a big deal. Okay, I was gonna state the theorem right there, but I think what I'll do now is state it right here so that they can be directly on top of each other in the whiteboard here. Okay, so let's try theorem 6.12. And this one, this is our last result, guys. This is the fundamental theorem of calculus. And this one is part 2. Okay, so seeing these side by side will be a good idea. So again, I'm going to let f be Riemann integrable from A to B. Start off with our Riemann integrable function f. But this time, I'm not going to use the antiderivative. Instead, I'm going to define a new function, capital F, that goes from the closed interval AB to R as well, via, and now how is this thing defined? Well, capital F of x is simply going to be the value of the integral of little f from a to x. Okay, so it's going to be the integral of f from a to x. Keep in mind, guys, that x will be somewhere between a and b. So if little f was Riemann integrable all the way from A to B, then it will also be Riemann integrable from A to X, because X is this is a smaller interval than the entire interval AB, right? So this makes sense is what I'm trying to say, right? This will make sense. Okay, so then capital F is continuous on the closed interval AB. That's the first little point. And if little f is continuous at some point C in this closed interval AB. So if little f is actually continuous, so we assumed that it was Riemann integrable, but if it's actually stronger than that, if it's actually continuous at some point within that interval, then capital F is differentiable at C. Okay, so if little f is continuous, then capital F will be differentiable. And what is the derivative of capital F at C? What is capital F prime of C? Well, it's exactly little f of C. Okay, so the derivative, what is this now? This is the derivative of the integral of little f. And it's getting us back to little f again. So the integral of the derivative of phi gets us back to phi. And now the derivative of the integral of little f gets us back to little f. So they're completely analogous results that of course make sense to put them here together. Let's do the proof of this one as well. And this one is not in the list for your theorems, but that doesn't mean you shouldn't try to understand it, because after all, there's a lot of stuff in this proof that's pretty helpful in terms of everything we've learned. Right, so let's see if we can try to understand this a little bit. Okay, so for the proof, last proof for our semester here. There's the first part of it is to prove that capital F is continuous, and I'm going to start with that first. And I'm just going to prove that using our standard good old definition of continuity. For all epsilon, there exists a delta such that if absolute x minus c is less than delta, then absolute f of x minus f of c is less than epsilon. So we're just going to go right to the definition, standard definition. So let's let epsilon greater than 0 be given, just like that. And I just want to point out that little f is bounded. So since little f is bounded, can somebody tell me why I know that little f is bounded? We're not assuming that little f is continuous until later in the proof. If we know that little f is continuous on a closed interval, it would be bounded there. But what's the other reason I know that little f is bounded even if it's not continuous? Because it's Riemann integrable, right? In fact, when we defined Riemann integrable functions, the very first thing we wrote on chapter 6 was, oh, the function is assumed to be bounded. So we're assuming that this little f is bounded because it's Riemann integrable. So what does that mean? That means that there exists some positive number, I'm going to call it capital M, greater than 0, such that the absolute value of, I'm going to just write it as absolute value of little f of t is less than or equal to this M for all t in the closed interval AB. We're not really going to use the t very much in the proof. It's just kind of a dummy variable for my function right here. Okay? So there exists some bound, capital M, and the absolute value of the function stays within plus or minus of that bound. Okay, fantastic. So I am now going to tell you what the delta is. I'm going to let delta equal epsilon over m. Okay, and let's assume that we have 2 points x and y. So let's say that x and y are in this closed interval a, b. And we may as well assume that x is less than y, such that absolute x minus y is less than delta. So I hope everybody understands that normally we would be stopping to do the scratch work to figure out what the delta is. We've done that so many times, right? Here, I've already done the proof before class. I polished it up. I've already figured out what the delta is that I need, and I'm just presenting you with the polished solution without the scratch work. So there's no scratch work in this proof. I'm just kind of saying, out of the sky, here's what the delta is gonna be that has to work, and now I just have to convince you that it really does work. Okay, now how do I convince you that it really does work? Well, I pick 2 points in the interval that are within that delta of each other, and then I'm going to look at how far apart are the f of x and f of y. This is how we go, and this needs to be less than, and by the way, it's capital F, because the claim right now is that capital F is continuous. So that's why I'm working with capital F. And I need this to be less than epsilon. That's what I need. I'm going to start by writing this in the opposite order, if this is okay. So I'm going to write it as absolute of f of y minus f of x. There's no reason I can't do that. And then I'm just going to feed in what the formula for capital F is. We have an integral from a to y of little f minus an integral from a to x of little f. So if I think about my interval, here's a, and then goes over to b somewhere, but I have x here and y here, right? So the assumption was that x was less than y. So what this is the integral from a to y minus the integral from a to x. What would that be equal to?
This is 2 and 2.
The integral from what to what? How about from x to y, right? Okay, so remember the integral from a to y can be thought of, just looking at this little picture, can be thought of as the integral from a to x plus the integral from x to y. That was one of our propositions in last class, I think, or class or two ago. So this integral here is just the difference of the other two. It's just the difference of the other two, looking at that little picture. Okay, then we have this result. I wrote it down and I promised a proof. I did a proof by postponement on Tuesday, which I said I was going to do in the review session, which is that I can now move that absolute value bar inside the integral. So let's erase this so I have enough room to finish this little proof. Okay. So this is less than or equal to the integral from x to y of absolute f. Okay, so that's by a result, I think it was corollary 6.1. So you can take a look in your notes. Again, I didn't prove it yet. I'll do it in the weekend review sessions as a nice little example. But guys, the absolute value of f is always less than or equal to m. So I can come in here and replace this with the integral from x to y of m. M is my bound on my function. Okay, and if I integrate a constant from x to y, I simply get that constant multiplied by the difference of the limits of integration, which would be y minus x. And y minus x, how far apart are x and y? Less than delta, right? So this is less than m times delta. M times delta, my friends, is equal to epsilon. That's what I wanted. That's what I wanted, so it's got a bunch of skinny little steps here, right? So the absolute value of f of x minus f of y is less than epsilon, isn't that great? So that proves that capital F is I'm not done with the proof yet. I proved this part. Capital F is continuous on the whole interval. By using a standard epsilon delta proof. For all epsilon, I can find a delta such that if absolute x minus y is less than delta, then absolute capital F minus capital Y, f of y, is less than epsilon. That's the first part. Any questions so far? This is kind of a good break point. Okay, I got the second part of the proof still to do, so let me erase and give myself enough room to finish it over here. I have to prove that if little f is continuous at C, then capital F isn't just continuous, it's actually differentiable at C. And we even know what its derivative is. Okay, so for the second part, so now, next, let's assume that little f is continuous at some point little c. That's the assumption, as you can see in the statement here, right? So assume that little f is continuous. See, I would like to show that capital F is differentiable at that same point c. Well, I'm gonna make a little claim here first. That is going to be kind of a subclaim to help us with that. And that subclaim is that if I take the limit as x approaches c, I'm going to write down something that's going to look like the derivative definition, right? I'm going to write capital F minus capital F, capital F of x minus capital F of c over x minus c. And I'm going to from that, I'm going to subtract f of little c. I'm going to claim that this limit is equal to 0 before I go any further. I mean, you can kind of see that this isn't that far from the conclusion that we want, because after all, the derivative of capital F at c is basically this part. And if you subtract little f of c and get 0, well then capital F prime of c is going to equal little f of c. So that's really the point. And again, the way I'm going to prove this claim is I'm going to take the absolute value of what's in here and show that it's less than every epsilon. So just like we did that trick on the earlier proof, to prove this thing, we subtracted the two sides, took the absolute value and proved it was less than any epsilon. I'm going to do the same thing here. Okay? So let's do that. To do this, or to show this, I'm going to let epsilon greater than 0 be given again. Here we go again, another epsilon greater than 0 be given. I really recommend you just literally adopt that exact language. Sometimes I see people saying things like for any epsilon, and then I wonder, well, is it fixed or is it changing? And then the word any is the worst confusing word of all time. I once went in, I was doing my PhD thesis, I went in to talk to this professor about my research, and he completely didn't understand. I had written my statement with like, for any, whatever it was. And he's like, well, does that mean for every or for some? Because if you think about it, it's a little bit of a confusing word. So really try to just really adopt this exact phrasing. I know I've always said, oh, as long as it's correct, I don't mind what you do. But just in terms of being totally clear with it, that's the best phrasing of all time. Can't misinterpret this. Okay, so with that in mind, I'm going to now try to look at the absolute value of capital F of x minus capital F of c all over x minus c and then minus a little f of c. I'm gonna try to look at this thing. Okay, so, this thing is going to be equal to the absolute value. I'm gonna actually pull out the x minus c from the denominator here. And then in the numerator, what I actually have is capital F of x minus capital F of c, right? So the numerator is the integral from a to x of f minus the integral from a to c of f. And then minus f of c. So remember, guys, capital F is defined in the statement here. Capital F of x is the integral from a to x. Capital F of c is the integral from a to c. And so that's literally what I have right here. And from there, I'm going to rewrite this as the absolute value of 1 over x minus c times, I'm going to do the same thing here, guys. This is a difference of integrals. So if I integrated from a to x, and now I'm subtracting the integral from a to c, it leaves me with the integral from c to x of f, right? And then minus, now this is f of c, that's a constant. Would you guys mind if okay, well, let me just do one step at a time. Just leave it the way it is. Okay, I would like to actually pull this absolute x minus c all the way out in the next step. So I can pull it out of the first term because it's already just sitting there. So that leaves me with the integral from c to x of f. But the question is, what about this part? Well, this would be f of c, you need to put f of c times absolute x minus c in order for the equation to balance. But I'm gonna view this as a constant, which it is, f of c is a constant, and I'm going to integrate 1, right, from c to x.
Did you do absolute values on that?
And I need absolute value bars. Yeah, you know what, you're absolutely right. This technically, instead of brackets, would look a little better if I put, that's what you meant, right?
Yeah.
Yeah, I should definitely have full-blown absolute value bars on that. Guys, don't let me get away with anything here. If there's a step that doesn't look good, let me know. Okay. So this is what we have. I'm gonna continue up here if you don't mind. So far, everything is an equal sign. So now I have 1 over absolute x minus c times the absolute value. Now, guys, I'm subtracting 2 integrals that have the same limits. So let's turn that into just a single integral from c to x of the difference that we have. So the difference would be little f of x from the first one minus little f of c in the second one. Is everybody comfortable, by the way, when I integrate 1 from c to x, I just get x minus c. So that x minus c cancels with this x minus c and just leaves me with the f of c. That's kind of how this step happened. Right? Okay, so now I've just simply, I basically just put this on the inside again. So I put the f of c in here. I have the integral of f of x minus the integral of f of c, and I'm writing it as an integral of their difference. Yeah, so that's all that we have there. And let's see. This integral here, because little f is continuous, little f of x minus little f of c, absolute difference of those is going to be less than whatever epsilon I want to use, right? So did I start with an epsilon somewhere? I sure did, right? So I'm going to let epsilon greater than 0 be given. So now, since f is continuous at c, there exists a delta greater than 0. Can you guys see over there okay? All right, I might end up having to go back over there. Let's see. there exists a delta such that if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than whatever I want. Right, and I want this whole thing to end up being less than epsilon. This part is controlled by the delta, so what I wanna do here is put, what do I wanna put there? I just wrote epsilon in my notes. Let's just see if this makes sense. So let's write epsilon there. I can always change that. I can always adjust that. I need to figure this out more. Oh, this last part is always a little tricky. Okay, so studied this very carefully. So, yeah, I think this is good because if I replace this integrand with epsilon and I integrate epsilon from c to x, that'll give me the x minus c times epsilon to cancel this x minus c, and it'll leave me with this whole thing being less than epsilon. That's exactly what I want. So let's just continue over here. So thus, if absolute x minus c is less than delta, then 1 over absolute x minus c times the absolute value of the integral from c to x of f of x minus f of c is less than 1 over absolute x minus c times the absolute value of the integral from c to x of epsilon. I'm just putting in the epsilon there because f of x minus f of c is less than epsilon. And this is 1 over absolute x minus c times epsilon times absolute x minus c, which is epsilon. So if absolute x minus c is less than delta, then let's give the big summary here. Capital F of x minus capital F of c all over x minus c minus little f of c is less than epsilon. And that epsilon was arbitrary. That epsilon was arbitrary, and so I'll just say, thus proving the claim. That proves the claim. Yeah, and the claim is that the limit of that expression as x approaches c is 0. Okay, so we've shown now that this difference is less than epsilon for all epsilon greater than 0, all fixed values of epsilon. For every fixed value of epsilon, I can make this number less than that epsilon. Okay, so if I can do that for every epsilon, then that means that this number is 0, right? So what is capital F prime of c? Well, we know the definition of it, guys. The definition of it is that it's the limit as x approaches c of capital F of x minus capital F of c over x minus c. And I can write that as the limit as x approaches c of capital F of x minus capital F of c over x minus c minus f of c, and then I'm gonna just add f of c to the end of that. So I don't think anybody's gonna quibble with me here. I just took what I had before and I subtracted f of c and then I added f of c. Didn't change anything at all, subtracted something and added something. But if I now insert some parentheses here like that into what I have, then the first limit is 0. And the second limit is, well, this is just a constant. F of c is a constant, the limit of a constant is just itself. So this is literally just 0 plus f of c, little f of c, which is little f of c. Whew. I think that does it. Always look big picture here, guys. Oh my camera. The derivative of capital F at C is equal to little f at C. How come? Well, because when we write down the definition of the derivative and we just take this fraction, this difference quotient, and we subtract and add the same thing and put parentheses around this much of it, that first much of it is exactly what's handled by the claim. The claim up there says that this difference here is 0. Okay, so that one is 0. This is just a constant that's added on now. So when you add those together, you just get little f of c. That look okay? So the derivative of the integral of little f is just little f again. At any value of c where the little f was continuous. Okay. I like it. Questions? Only took us 15 weeks to get to the point of being able to prove this, but you do notice in the 2 proofs that we did, there was a fair amount of use of things we did earlier, right? Stuff about the definition of continuity, right? Working with limits, breaking up a Riemann integral into 2 parts. That's something else we did a little more recently. Playing with absolute value bars. It's all kind of a nice culmination of things coming together. Yeah, so, okay, I tell you what, guys, let's take a 10-minute break. After the break, we'll have about a half hour to do some review for the final, which is going to be partially in the form of a group work that I'm going to let you guys work on. So during the break, I'm going to be drawing a big diagram on the board, and then I'll explain it when we come back in 10 minutes. So go ahead and get some fresh air though, if you'd like.
Saw the diagram.
So that's easy.
Well, it actually makes sense. It makes a lot of sense. Yeah, yeah.
So, but that's
Oh,
dx dc. Then down here, all of a sudden it becomes a dx.
Well, this is just the same kind of idea. We have a here, we have c here, we have x here. So the integral of from a to x of f is the integral from a to c of f plus the integral from c to x of f. So what I did is I took this one minus this and just got this guy minus this guy. And so that's how I'm going from here.
Yeah, so we're starting with C,
C.
going to X,
Correct.
that's how you're able to make it to X here.
Oh, yeah, yeah. Well, when I write, this is just, I don't even need that really. I just wanted it to be clear, that's the function f. It's the same f that we had here. It's just, I wanted it to be clear that this is still my function, so it is actually not a constant, it's depending on x. So I put that little of x in there. I kind of, yeah, that was a subtle point.
Gotcha, because here it was depending on C.
Oh, this could be x too. The c is just the limit of integration.
Gotcha.
Yeah, the limit of integration. So, yeah, that's true, but what is capital F of C? Capital F of C is the integral from a to c of little f of x. So I could take this notation and feed it in there perfectly by just saying, all right, when I've got capital F of C here, that means the integral from a to c of little f. But I have to understand that if I gave you a little f, I might give you something like this. Right, that would be your little f. That would be a function of x that's inside of you. So we just don't always emphasize the X there, but I wanted to do that here so that I can talk about the continuity definition.
I was just hurting my head. how-
Yeah,
A
that's,
C and an X goes down to an X.
good point, good point.
Right.
Yeah,
Thank you.
the X is in here, it's just being suppressed,
Gotcha.
abusive notation, call that.
Start calling Dr. Wilson.
Right, get straight.
this for you.
Please, just kidding. Don't give me a
It
heart
doesn't
attack.
work on you guys anymore, but I tell you what, in my 250B class, the first time I do it every semester, it purifies the pen. Play that game with it and watch them swirl.
Oh.
That's not the nicest stuff, Annie.
Fine.
He says I do, but he's still gonna.
Niceness was never mine. Still, for sure.